Good morning, everyone. I am Richie Montalban, and I am the first reporter from the Group 4. And for today, we're going to discuss about the Chapter 4, which talks about soil test and survey. Test for particle soil. A different soil has different characteristics affecting the performance of each individual soil by moisture content and density. There are several kinds of physical tests that have been developed to measure soil performance, issued and recommended by AAASHTO and ASTM. Sieve analysis is the process being used to determine the particle sizes of gravel and fine aggregates. A sample of material is thoroughly dried and shaken through a series of sieves ranging from coarse to fine. The amount on each sieve is weighed and recorded. The AAASHTO standard sieve sizes for soil aggregates are presented as follows. Material finer than number 200 sieve or 0.075 mm is not feasible in determining the particle sizes. Instead, these are determined by observing the rate at which the grains settle through liquid or gas. Under the Stokes law, the rate of settlements of solid through a given liquid or gas is proportional to the square of the diameters of the solid. The AASHTO method as specified is called hydrometer test. AASHTO designation T88. Hydrometer test. First, sample of the material passing number 10 sieve is mixed thoroughly with water and dispersing agent that dissipate any electrolytic bonds in the sample that might cause flocculation and accelerate settlement. Second, after 12 hours, the mixture is agitated, making all particles suspended in water. Third, the mixture is then placed in a graduated flask, allowing the solid to settle under the pull of gravity. Fourth, the bigger particles settle first, followed by the smaller, then the smallest one. The specific gravity of liquid decreases. The changes are recorded by special hydrometer and read at prescribed intervals. Fifth, change in specific gravity is related to the grain size of the material by Stokes' law. 6. Careful control of temperature and other possible variables is strictly observed to obtain satisfactory test results. Next is test to evaluate the effect of moisture. Consistency of the soil varies from semi-solid to plastic, then to liquid if water content is increased. First is the liquid limit test. The AASHTO designation T89 on liquid limit signifies the percentage of moisture at which the sample changes by decreasing the water from liquid to plastic state. When the sample is wet, then the liquid limit, a grooved sample of the soil in a cup, will flow when lightly jarred 25 times. On the other hand, if the sample is jarred at the liquid limit, water separates the soil particles just wide enough to remove the soil mass sharing strength. Several tests on each sample are required to reach the moisture content wherein the groove in the sample is required to close at exactly 25 blows. Second is the plastic limit test. AASHTO designation T to 90 signifies the percentage of moisture wherein the sample changes with lowering wetness from plastic to semi-solid condition. So, at this stage, The soil mortar starts to crumble when rolled into threads 1/8 diameter. Then additional water will make the soil plastic, but sands are non-plastic material that its non-plastic limit cannot be determined. The plastic index text. AASHTO designation T291 is defined as the numerical difference between its liquid limit and its plastic limit. It is also referred to as the percentage of dry weight in some combination. Then it measures the fineness and the shapes of the soil particles, the interplay of the attractive forces tending to hold the clay mineral flakes together, the thickness and velocity of the water flow, and the quantity and electrical charges of the cations. For coarse grain soil or fine grain soil with few particles of clay of colloidal size, small increase of water above the plastic limit will cause particle separation, destroying the attractive forces that provide shearing strength. It simply means that the difference between the plastic limit and the liquid limit is small, so that the plastic index is also small. On the contrary, for a soil that is high in clay or colloids, more water will be required before the attractive forces and overcome and the strength of the mass is destroyed. In this case, the plasticity index is numerically high. Experienced road builders use the plastic index as one control in selecting the materials for underpavement. A common base coarse material specified requires the plastic index not to exceed 6, while others insist on not greater than 3. Soils with high plasticity indices are much less acceptable for subgrade and base course. Next is the shrinkage test. Shrinkage test measures the changes in volume and weight that occur as partly mixture of soil and water, except sieve number 40. Sample is dried from the near liquid limit to constant weight of 110 degrees Celsius. Then the results are stated in terms of shrinkage limit, volumetric change, and lineal shrinkage. Higher value of shrinkage factors show that the soil will give more trouble and problem. The volume of a certain soil increases when it absorbs water. Soils that are suitable for subgrade and base course are those that expand very little when moistened, and those that swell more are considered as poor materials. A common soil specimen requires volume change limit of 1% for base course materials. Hand feel test. Experienced soil engineer employed the hand feel test to approximately predict the plasticity index of the soil. The test may include thread toughness at moisture content and approximating the plastic limit, the air dried strength, dilatancy. Soil mortar possessing high plastic index will produce tough, tough threads and high strength without dilatancy.
Density test of soil. The density of soil or weight per cubic foot varies with the peculiarities of the soil itself, the moisture content in the compacted device plus the method of their use. The standard weight of soil per cubic foot cannot be fixed but should be determined in particular instance. The main variables in the soil proper are specific gravity of the soil particles, particle size distribution of the soil, grain shape of soil particles. Specific gravity of soil particles that may vary from 2 to 3.3, that is normally between 2.5 and 2.8. Particle size distribution of the soil, a mass composed of entirely spheres of one size in the densest possible condition will contain 75% solid and 25% voids. The smaller the sphere in the mass, the higher the percentage of the solid. Hence, particle size distribution may greatly affect density. Grain shape of soil particles. Sharp angular particles will resist shifting from loose to a compactive state. Flaky particles in soil will decrease its density because they are difficult to compact. Laboratory tests for soil density. Tests for density may be divided into two. First, laboratory tests to set standard for density. Second, field tests to measure the density of soil in place on the roadway. Laboratory tests may be divided into three according to the basis of compaction procedures. First, the static test. Second, the dynamic or impact test. Third, tamping, foot, or kneading compaction test. Static test is determining the maximum density of soil sample in the laboratory. The dynamic or impact test, samples of soils each containing a designated percentage of water are compacted into layers into molds of specified size. The sample is compacted by applying a number of blows from a free-falling hammer of prescribed dimension and weight with flat circular face. And then the peak of moisture density values represents the standard density. The ASH2 test may be applied on that portion of the soil which will pass number 4 sieve or all that passes 3/4 sieve. Tamping foot or kneading compact test. The material is fed into a rotating mold and compacted by several repetitive loads applied through tamping shoe shaped like a sector of the circle. About 25% of the specimen is covered in each application. Compaction is through kneading action is contrast with the static pressure or impact test. Field density and moisture content by sampling. The manners of determining relative compaction by sampling are as follows. First, obtain samples of the compacted materials to be tested at full depth. Second, find the wet and dry weight of the sample, then determine its moisture content. Third, determine the volume of sample in the field by finding the weight of materials required to fill the shape space. From the dry wet of the sample, there are 4 factors that affect the accuracy of measuring relative density, and they are change in the soil itself. Second, the sampling methods. Third, the accuracy of laboratory testing for standard density. And last but not the least, the accuracy of testing field density.
The strength test. Soil test to determine the strength of soil is classified into 1. Test for load carrying capacity, rate, and amount of consolidation in soils that support the foundation. 2. Test to measure the supporting power of disturbed soils as compacted under standard procedure. California Varying Ratio Method or CVR is performed in construction materials laboratories to evaluate the strength of soil, subgrades, and base coarse materials. with an empirical design chart to determine the thickness of pavement base and other layers. The tests are briefly conducted as follows. 1. Disturbed soil samples at different moisture content are compacted in 3 layers by static loading or impact hammer into a cylinder mold 6 inches diameter by 8 inches high. The specimen depth is about 5 inches. The 5.5 pounds hammer ASH2 standard density test is used in the impact method. 2. The moisture density curve is flattened. The sample with greatest dry density is chosen. 3. The specimen in the mold is immersed in water for 4 days to allow saturation. Expansion of the specimen is recorded. 4. A small piston of 3 inches diameter is forced into the confined specimen. Load deformation data is recorded. The California bearing ratio is computed as follows. CVR equals load of test specimen 0.1 in piston penetration over load carried by standard crushed rock based on 0.1 inch piston penetration. Procedure in finding CVR of soil. Step 1. Compact by static pressure or by impact. Step 2. Graph and find maximum density. Step 3. Soak in water. Step 4. Apply load. The beam stabilimeter method is a triaxial testing device used to determine the stability of bituminous paving mixtures, soils, and other plastic or semi-plastic materials. Stabilimeter operating procedures. 1. Four different samples are prepared on a search cylinder, about 4 inches diameter by 2.5 inches high of different known moisture contents. 2. Compaction is done using tamping foot or kneading compactor. 3. Each compacted specimen inside the mold is compressed until water exudes from it and passes several electric circuits wired in parallel through the base plate of the exudation measuring devices. Diagram of the beam stabilimeter. It was found out after several tests. The soils in underlying pavements exceeded moisture under pressure of about 300 psi. It appears that soaking did not produce a condition of a certain fine grain materials. In effect, the exudation pressure is a different means in determining the moisture contents of the soil on the roadway. Moisture content in stabilimeter test samples is set to bracket the 300 psi value on which design was based. Test for expansion pressure. After exudation test, while sample is still in the mold, it is tested for expansion pressure after perforated brass plate is placed on the sample and covered with water for 16 to 20 hours. Expansion during this period is prevented and the pressure that prevents it is measured. As mentioned earlier, soils that expanded due to the presence of water should be placed under sufficient weight of fill to prevent swelling.
Stabilometer test. These test methods provides a produce for determining the relative stability. Stabilometer value of asphalt concrete by measuring the horizontal pressure developed in a compacted test specimen under the given vertical pressure. After the expansion test, the specimen is enclosed in a flexible sleeve and placed inside the stabilometer. Vertical pressure is applied slowly at a speed of 0.05 inch per minute until it reaches 160 psi. The developed horizontal pressure is reduced to 5 psi using the displacement pump. The turns of the displacement pump are needed to bring the horizontal pressure to 100 psi. This displacement produce is intended to measure the penetration of the flexible diaphragm into the intersection of the sample. The resistance value R of the soil is computed by the following formula. R equals 100 minus 100 all over 2.5 PV all over pH minus 1 plus 1, where R is the resistance value, PV is the vertical pressure, the value of 160 psi, D is the turns displacement reading approximately from 2 to 5, and pH is the horizontal pressure in psi at PV of 160 psi. Triaxial design method. This method is used by some agencies for compression tests. In this open system triaxial test, lateral pressure is held constant releasing from the container as the increased load causes the sample to expand laterally. Dynamic modulus. Recompacted or undistributed sample are tested to determine the influence of temperature, degree of saturation, density, and age of the dynamic response of the pavement materials. Modulus of asphalt concrete ranges from 100,000 to 1 million psi depending upon temperature. Modulus of cement treated base ranges from 500,000 to 3 million psi. Modulus of aggregate base and sub ranges from 10,000 to 50,000 psi. Modulus for fine-grain aggregate soil ranges from 1,500 to 50,000 psi depending upon water content. Nuclear device test. Nuclear devices for determining in-place densities and moisture contents are used. These gauges readings are easily converted to density and prevent moisture using calibration curves or microprocessors. The portable device is either the transmission or the backscatter type. As you can see in the figure 4-6, it shows that the schematic diagram of nuclear devices transmission type. In figure 4-7, it shows that the schematic diagram of nuclear devices backscatter type.
Thank you, Mr. Vasco, and now let us move on to soil survey. The preliminary soil investigation is an integral part highway reconnaissance and preliminary location survey. In fixing the position of the roadway, the following should take it into account. First is the soil condition. Soil condition can be defined as the capacity of a soil to function within land use and ecosystem boundaries and to sustain biological productivity. Second is the directness of root. Root directness is the ratio of the root distance to the straight line distance. Third is the topography. It is the surface of the soil and its relation to other areas. Next is the right of way. Right of way is a type of survey which maps the limit of existing or proposed highways or public utility transmission easements, including the mapping of parcels to be acquired for such purposes as referring to an established baseline. Next is the neighborhood disruption, environmental consideration. Environmental consideration, it is a natural part in all we do in our forest. It encompasses the nature conservation consideration and cultural heritage consideration. The early phase of soil survey is the collection of information gathered from the following. First, identification of soil types from geological and agricultural soil maps, aerial photographs, and other sources. Second, investigation of groundwater conditions, examining existing roadway cuts and other excavations. Third, review of the design and construction procedures and present condition of roads that traverse the area. Fourth, soil exploration along the right-of-way using auger boring and test pile. Sampling should be at frequent intervals to fix the boundaries of each soil types. Fifth, these holes should extend to a significant depth below the subgrade elevation with recommendation minimum depth. Next is the location, nature of the ground, origin of the parent materials, landform and agricultural soil name should be recorded. And each soil layer is described according to thickness, texture, structure, organic content, relation contents, and cementations. The depth of seepage zone of free water table and bedrocks are also recorded. And the soil profile along the roadway center line showing location or test hole range of soil profile characteristic for each distinct soil gap is plotted. Along with the first reconnaissance and preliminary location survey, the highway agencies make a detailed study of the following data. Number 1 is the vertical and horizontal location of the proposed construction. The main difference between horizontal and vertical construction is how the two types of structures exist spatially. Horizontal construction is a typical wider and lower to the ground. Vertical construction is higher. Vertical construction project includes skyscraper and high-rises. Location and evaluation of suitable barrow and construction materials. This means that barrow or suitable roadway excavation materials including organic and evaluation of site-specific condition and surrounding soils. Third is need for the type of subgrade or embankment foundation treatment and drainage. The subgrade course is typically the natural soil as well as chosen particle size aggregate which is compacted to specific levels. An embankment refers to a volume of earthen materials that is placed and compacted for the purpose of raising the grade of a roadway or railway above the level of existing surrounding and good surface. Fourth is the need for special excavation and dewatering techniques. There are 4 main dewatering methods used in construction. First is a well point, educator wells, sump pumping, and deep well point. Fifth is the development of detailed subsurface investigation for specific structure. And the last is the investigation of slope stability in both outs and embankment. Refraction seismic method, a geophysical method used for subsurface exploration called refraction seismic method, relies on the principle that the speed of shock traveling through the Earth's surface varies depending upon the kind of materials. Shock waves travel through light lost soils at approximately 180 meters per second and 6,000 meters per second on dense and soil rock. If the Earth's crust is of uniform material for some depth, these time intervals are proportional to the distance from the origin of exploration. If the surface layer is of harder dense material, the time interval to a distant point is shortened. The records for the time of wave travel against the shooting distance, the number and thickness of different underlying layers, including the deep to bedrock, can be predicted. This test is used in determining the depth of the rock but could be deceiving in unruly tilted stratified materials. The refraction method was developed for exploration of underground condition of roadway cuts. The resistivity changes where dip is produced, recording the result of various electrode spacing. This method is somewhat reliable, although sometimes it cannot be totally dependent on regarding the information as to the presence of solid rock. It is useful in area exploration when it is used to find localized sand and gravel deposits. So that would be all for Group 4. Thank you and have a great day.